All right, now we are going to see one final example of Fourier series, continuous time Fourier series. The next chapter will be discrete time Fourier series, and you won't be responsible in the midterm from discrete time Fourier series because we are not starting. But you will be responsible for all the things that we have seen regarding the continuous time Fourier series, including filtering. Okay, be very careful about filtering. I certainly ask questions about filtering a periodic signal. Therefore, how do the Fourier series coefficients pass through low pass filters, high pass filters, or any shape of filters that are represented on the frequency axis? That's a hint from me to you. Now, in this example, we are given some indirect measurements from some sensors. You see, in scientific measurements or data acquisition, imaging, etc., people may think that you just take a photograph of something and you show it, or you just put a microphone and record an audio or some signal, and that recording is there. Usually that's not true. You have to make some indirect measurements, and from those indirect measurements, you construct your signal and estimate which parameters have which kind of values, etc. That is actually a signal reconstruction that is going on in many cases. For example, you must have seen a photo of the black hole in a proximity galaxy, in a nearby galaxy. They have taken a photo, a picture of it. And that picture was not obtained from a telescope with very high resolution or anything like that. It was from a lot of measurements. And from those many measurements, they just reconstruct the information from there and here, and they put all together the data and the information to deduce something. And that image is a solution to those informations. For example, you may also know, for instance, computer tomography, where a slice of your body is shown on a biomedical image. It's not X-ray, because X-ray is a direct imaging where the X-ray beams pass through your body, and there's a sensor like the CCD sensor, that this time it's an X-ray sensor. From there, that imaging is reconstructed. It is still a reconstruction, but it's almost a direct imaging. But computer tomography is not like that, because it gives you a slice of your body. Do we cut you to take the photo? We cut you with a lightsaber, for example, from Star Wars. I cut you, and then I take a picture of your belly, and then I connect you again. That's not, of course, how we take the picture of a slice of your body, a slice of your head or your leg, etc. It doesn't go on like that. There are other measurements, and from those measurements, we make a deduction. We deduce that this must be the profile of your slice. That is therefore a very common practice in real life. This is a reduced and small example about how that kind of an information fusion collection can be done. Suppose that we are making some measurements, and we are making some assumptions as well. And the assumptions and measurements of a signal that we are unable to record directly is given like this. The signal is x of t, and we know that, so this is our assumption, it is real. It's a very good assumption, by the way. It helps you to think that the Fourier series coefficients are complex conjugates of one another, at least. We know that. AK is A minus K's conjugates. The second, it is periodic. That's also a good assumption or a good observation. And somehow we managed to determine the period. Maybe from peak to peak, we are able to make a measurement, and the distance between two peaks happened to be 4, let's say 4 seconds. This tells us that the period is 4, but within this period, we don't know the shape of this periodic signal. That is the thing that we are trying to reconstruct. And since it is periodic, we have Fourier series coefficients, AK. Okay, because for periodic signals, we have Fourier series coefficients. And the third one, by passing through a low-pass filter, we observe that AK is equal to 0 for K greater than 1. Because for K greater than 1 in magnitude, or less than -1, let's say, in terms of the indices, the higher indexes correspond to higher frequencies, and the signal does not contain high frequency. By passing through a low-pass filter, we make a template matching and see that actually it loses nothing. For instance, I'm just inventing a reasoning behind this, but this is just a toy example in a way. This is not a real practical experiment that has happened, but it could be. The fourth one is we don't measure the signal, but we measure a reflection of the signal. It's like looking at an image from a mirror. And the mirror essentially alters the phase of the signal. That's also very practically encountered. So instead of x of t, we observe y of t kind of thing. See some properties of y of t whose Fourier series coefficients are bk's. So xt has Fourier series coefficients ak, and yt with Fourier series coefficients bk are related to a minus k e to the minus j pi k over 2. This is given to you because of the system that generates y of t from x of t. It's like a mirror. Okay, that mirror is altering, it's reflecting the signal and altering the phase, which makes this kind of an indirect measurement. And we observe y of t to be an odd signal. So around 0, it is antisymmetric. Y of t is observed to be odd. It's an indirect measurement. Clearly, somebody was constructing this question just to make a toy example. It's for torturing purposes. It may or may not make sense in practice. And we are also able to have a photodiode or something like that, where we measure the energy, or sorry, the power of this y of t, which is the same as the power of x of t, by the way, because the relation between y of t and x of t is just a phase shift and flipping around kind of a relation. So the power of y of t is measured, and it also gives you the power of x of t. So I can directly write like this. Power. The 4 beneath the integration means from 0 to 4, or from -2 to 2, or from -1 to 3, etc. The integral duration is 4, which is the period, as you may know. Magnitude x of t square dt is equal to 1 over 2. So this is the power, the average power of your signal. So these are known. From these, can you write the analytical formula of x of t? Just tell me what x of t is. Without any further rumination and thinking about it, I can clearly see that since there are only 3 Fourier series coefficients, because for k in magnitude greater than 1, the Fourier series coefficients are 0. So there is a minus 1, a0, and a1. And it means that x of t is a sinusoid. And because it's real, it must be a sinusoid with some phase maybe. It may be a sine, it may be a cosine or something in between. And I just want to determine what are the, what is the scale of that function, cosine or sine function, sinusoid, and what is the angular shift. And yeah, that's all actually. From all these, I want to say about that. So I can see that we have only a minus 1, a 0, and a 1. Okay, this is one observation. And another observation, since period is 4, omega 0 is 2 pi over 4, which is pi over 2. Okay. So with these two, I can say that x of t is therefore a0 plus a1 e to the j pi t over 2 plus a minus 1 e to the minus j pi t over 2. But I don't know what is a0, what is a1, and what is a minus 1. Now, let's say that y of t, whose Fourier series coefficients are bk's, is given to us in 4, number 4. We know we are given this. But I can think of this. A minus k must correspond to x of minus t, okay, from the properties that we have seen. So since there is an a minus k here, it means y of t is x of minus t plus something or minus something. But what is that? E to the minus j pi k over 2 is, by the way, it's also equal to e to the minus jk omega 0, because omega 0 is pi over 2. So here I can see that there is a scaling of minus 1 here. So this is a shift. It corresponds to a shift by 1, x of t minus 1, sort of thing. We'll make this kind of a multiplication for y of t. So this bk must be referring to x of minus, in parentheses, t minus 1. Okay. Which can also be written as x of minus t plus 1. You may want to verify what are the Fourier series coefficients of this time rotated and shifted version signal. If x of t has Fourier series coefficients ak, what are the Fourier series coefficients of this new thing, x of minus t plus 1? And you will find it to be equal to this. So this is y of t. And it is given to be odd. So this sinusoid is an odd function. What is an odd function? An odd function is a sine wave like this, which goes on, or its opposite, or something like this. These are sines are odd functions. Cosines are even functions. We know that. So this y of t is an odd function. It means it's a sine function, and it cannot be sine of something plus a, or plus a value, or minus a value. The zero level, the DC level of a sine wave, in order to for it to be an odd function, must be 0. So the DC, let me put it like this: DC of y of t because for odd functions, the DC value is 0. And since it is a flipped around and shifted version of x of t, it also tells me that DC of x of t is also 0, which means a0 is equal to 0, which is here. So there is no a0. There's only a1 and a minus 1. If a0 is non-zero, then by flipping around and shifting it, it wouldn't make a y of t, which is an odd signal. There's no such possibility. So a0 must certainly be equal to 0. So we found one of them. A0 is 0. And also B0 is also 0. Let me also indicate it. So B0 is 0. So that's why A0 is also 0. Now, we also have, since it is an odd function of y of t, b minus 1 must be equal to minus of b1, because odd functions have only imaginary Fourier series coefficients, like a sine. You remember that? What were the Fourier series coefficients of sine of omega t? It was 1 over 2j and minus 1 over 2j. So they are negatives of one another. They are imaginary and they are negatives of one another. So b minus 1 is equal to minus of b1. But I don't know what is a1 and how it is related to a minus 1. Because it depends on what kind of a shift we are talking about. You remember that the period was 4. So let's continue with this position here. This is minus 2, and this is 2, right? For a sine or a negative of sine, this is the point that I indicated at the left is minus 2, and this zero crossing point is 2. Now, if I shift this by 1, if I flip it around, it will be the other sinusoid. It will be either the blue or the red sinusoid. We don't know which. But it's going to be, when we shift, it's going to be a cosine. Or this cosine, a negative cosine. Sure. So in short, x of t is this kind of a cosine form, where this is 2, this peak is 4, and this is minus 2. Okay. So we are almost there. We are trying to find now, we observe that x of t is either a cosine or a negative cosine, but what is the size of that cosine? For that, we have to use the famous Parseval's relation, because the energy is given to you. We are given that 1 over 4 integral within a period y of t squared dt is equal to 1 over 2, which is the same as saying 1 over 4 within a period of 4, x of t squared dt is equal to 1 over 2. These two are the same things, because we are not scaling our signal. We are just flipping around and shifting, so the energy does not change. And this energy is defined in time, from where we can see that b1 square plus b minus 1 square, which is the power in Fourier series from the Parseval's relation, which was property number 7 from our previous notes, is equal to 1 over 2. And we know that b1 is equal to minus of b minus 1. It was here. So we have 2 of b1 square is equal to 1 over 2, saying that b1 is equal to square root of 1 over 4, which can be plus or minus 1 over 2. So this is, that's the magnitude, by the way. Magnitude of b1, so it can't be negative, excuse me. I was being a little bit, I was hurrying, but I shouldn't hurry. b1 is equal to 1 over 2, but we know that b1 is purely imaginary, because that's only when b1 is equal to minus b1, because y of t is an odd signal, its Fourier series coefficients are purely imaginary. So what is an imaginary number whose magnitude is 1 over 2? Can somebody write an answer here or tell me by opening the microphone? Tell me an imaginary number whose magnitude is 1 over 2. I'm still waiting. And nobody is answering my question. Let me repeat the question. Tell me an imaginary number whose magnitude is 1 over 2. Do you know how to find the magnitude of an imaginary number? J times 1 over 4. Almost there, but why did you say J times 1 over 4 or J over 4? It is J over 2. The magnitude of the imaginary number J over 2 is 1 over 2 because the magnitude of J is 1. Okay, so B1 is essentially J over 2, but with a plus or minus. Both of them will have a magnitude of 1 over 2. Okay. By the way, do you know the magnitude of e to the j omega t? Because it's a complex number, therefore it has a magnitude. What is the magnitude of this? Do you know it? Because I'm now a little bit worried about whether you really know at least some minimal amount of complex numbers. What is the magnitude of e to the j omega t?
Hocam karekök içinde cos omega t'nin karesi
Uh-huh.
sin omega t olması lazım hani. Onun karesi.
Yes, it's correct. So what is it?
1.
Yes. 1. E to the j something's magnitude is 1. It is just an angle that rotates with an origin. It is just rotating, and it's the radius of that rotating circle is 1. For as t runs from minus infinity to infinity, it's just rotating. It makes a rotation, nothing else. This is something out of context. I was just curious whether you really know this or not. So you may just ignore it if you wish. But coming back to this one, B1 is plus or minus J over 2. And or plus and minus 1 over 2J similarly. It's just the same. That's a pure sinusoid, by the way, sine wave. But is it a minus sign something or a plus sign something? And that is something that we do not know. And when we shift that, so the magnitude of sine is 1. If the Fourier series coefficients are 1 over 2j and negative of it, but we don't know which is negative, which is positive, at the right or at the left, we don't know, B1 or B minus 1. One of them is negative, one of them is positive. And for that, it corresponds to a sine. So here in this graph, this is a sine wave with magnitude 1. It gives us, therefore, or minus 1. it is either the blue or the red one. Therefore, the shift by 1 will give us this black cosine term as x of t, or the blue cosine term as x of t, and that is something that we do not know. So it is the answer is eventually x of t is either plus or minus of cosine 2 pi t over 4. 2 pi t over capital T, which is plus or minus cosine pi t over 2. So that's it. This is the final result that we determine. We are able to determine x of t, therefore, up to a sign factor. We don't know the sign of it. It is either plus or minus, but with these 5 inputs, we cannot determine that. Whether its sign is a plus or a minus, we don't know, but we can say that this information is compatible with an x of t, which is either plus or minus of x of pi t over 2. Now, I gave you this example to give you an idea, an impression about the fact that in some cases in real life, we just observe some side information, indirect measurements and observations we make, and from those indirect measurements, we have to construct our signal, and this is what we did in this particular example. Clearly, there are several other example questions in the book and in other books as well. In most of the books that you may find other than Oppenheim's book, you will see that the Fourier series coefficient calculations are done in terms of not complex exponentials, but real sinusoids. But we have 2 different Fourier series coefficients then. One of them is the coefficient for cosine term, the other one is for the sine term. I may, for example, recommend that you go and check some other books, some other resources from the internet maybe, or you may find books, printed books. Solve the questions according to the knowledge of complex exponential solutions that we did in this class, and compare them to the result that is given in the book, which gives you a cosine and a sine term. See if they actually correspond to the same result or not. That would be a very good exercise. But before that, it's always wise to solve the questions in Oppenheim's book, end of book chapter, regarding continuous time Fourier series. This is where you will be responsible. After the examination, we will start seeing the discrete time Fourier series, and then it will be short. I'm not very much keen on or interested in discrete time Fourier series because it is something that is even more important in digital signal processing. Discrete time Fourier series is also known as the discrete Fourier transform, which is also implemented in computers using some fast algorithms, and the name is fast Fourier transform. So FFT and such things, the fast Fourier transform, are all discrete time Fourier series. So we're not going to spend much time about it. We are going to cover it, but it won't be as detailed as this continuous time Fourier series discussion that we did. It will be faster. Then we will continue with the Fourier transforms in continuous and in discrete time. Then we will proceed to the Laplace transform. Then we will do sampling, which is a domain conversion from continuous time to discrete time. And then we will see the Z transform. The Laplace and the Z transforms are extensions of Fourier transforms in continuous and discrete time. And that's about it. We will mostly see those things throughout this course. So we are finished with continuous time Fourier series. If you have any questions about the discrete time Fourier series, we may try to answer them. Yeah, I think there are no questions. If you have any questions, by the way, my screen is now a little bit disturbed. I'm unable to see the chat. I cannot move. So I will stop at this point and we will continue. Not next week. Next week on Monday, we have no class. On Wednesday, we have an exam. You may ask questions until then by email, by writing something on the Facebook page, if you wish, on Canvas. All the medium is available to us. So good luck in your examinations. Until then, I have to say bye-bye to you.